Very good afternoon, students. In today's class, we are going to learn about pumping lemma. Just to remind you all about last week's class, we had completed the two mechanisms or two processes for minimizing a DFA. We had seen the equivalence method, and we had seen the Hill-Nerode theorem or table filling method for minimizing a DFA, right? So actually I had taken a live class for equivalence theorem, but could not take a live class for Hill-Nerode theorem. So hopefully you all have seen the video and have understood how the thing actually works. Okay. Additionally, I had also discussed the few closure properties of regular language. That is under which operation regular language is closed, and we have seen that under union, intersection, reversal, then difference, clean closure. Under all of these operations, regular language is basically closed. That is, if we perform intersection of two regular languages, the resulting language will always be a regular language. In the same way, if we perform a union between two regular languages, the resulting language that we get will always be regular. So like this, I have mentioned the different operations under which your regular language is closed, and I guess I have also posted the material for the same in your Google Classroom. So if someone has missed it out, please I'll request them to go and check it, because these closure properties are really important part that all of you should know. Okay, so in today's class, as I was saying, we are going to start with pumping lemma. So what is pumping lemma? Basically, it is a theorem or a lemma which is used to check or used to prove that a language is not regular. Okay, so we will see the statement of the theorem, and then we will be seeing a few examples that if a language is given, how to prove that it is not a regular language using this pumping lemma. Okay, so let me share my screen. So my screen is visible, right? And am I properly audible?
Yes, ma'am.
Okay. So as I was saying, a pumping lemma is used to prove that a language is not regular. On the contrary, it cannot be used to prove that a language is regular. So we can never use a pumping lemma to prove that a language is regular. The reverse is true. That is, we can prove that a language is not regular. Okay. Now what is the theorem of this or what is the statement of this pumping lemma? Now if A is a regular language, suppose A is some language which is regular, then A has a pumping length P such that any string S where the length of S is more than is equal to P may be divided into three parts. What are the parts? X, Y, Z, such that the following conditions must be true. So these are the conditions. As you can see, the first condition is x, y raised to the power I, z is an element of A for every I greater than or equal to 0. Length of y is greater than 0 and length of x and y together is less than is equal to P. So if a language is, basically if we have to prove that a language is regular, then these conditions should be satisfied under pumping lemma. So if A is a regular language, then again we have a pumping length. The first step that we move is we decide a pumping length P such that any string of that language having the length P or greater than P can be divided into three parts, and then after that these three conditions corresponding to that particular string of the language A must be satisfied. If all these conditions are satisfied, then only we can say it is regular, otherwise it is not regular. Now in the very starting I have just said that we use pumping lemma to prove that the language is not regular. So how to prove that? What are the steps to prove that a language is not regular using a pumping lemma? Okay. So to prove that a language is not regular using pumping lemma, we basically use the contradiction theorem. That is, we start with the assumption that A is regular, and then at the last step we will find some contradiction and we will conclude that okay, since the conditions are not satisfied, A is not a regular language. So the first step is assume A is a regular language. As I said, it's a proof by contradiction. After that, we will set a pumping length. We will assume some length to be pumping length, and we will consider a string of this language A whose length is equal to or greater than P. It's just what is written in the statement of the lemma. After that, we divide S into 3 parts x, y, z, and then what we do is we raise y to the power I, and we try to get a string of this form and show that it is not a part of A. That is, it does not belongs to A, which is a regular language. Okay. And once you can show that this x, y raised to the power I, z is not an element of A, we can say that okay, so the language is not regular. Moreover, what we can do is we can also try out these other two conditions and check whether these conditions are satisfying or not. Many cases we will see that these conditions are also not getting satisfied, and after seeing this we can conclude that S cannot be pumped.
Hello, ma'am.
Yes.
I cannot hear you.
Just a second. Am I audible now?
No, ma'am, still cannot hear you.
Can nobody hear me, or is it a problem from your end? Just a second. Hello, hello, hello.
Ma'am, you're audible.
I am audible, right?
Yes, ma'am.
Okay. So I guess there is some problem at your end. You can leave the meeting and join again in that case. Okay. Yeah. So as I was saying. What we need to do in the last step is we need to contradict these three conditions. This one, and this one, and once we contradict this three conditions, we can say that our assumption was wrong and A was not a regular language. So these are basically the steps we need to follow, and maybe this is not so clear right now. Once we take an example and test it, I think it will be more clear to all of you. Okay. So now this is an example where we have a language A to the power I and B to the power I, and we have to prove that it is not regular using pumping lemma, right? So first of all, what was the step? We have to assume that the language is regular. That was the first step. So if you see here, the first step was assume A is regular. So that is what we are assuming here, that L is regular. Next we have to define a pumping length. So what will be the pumping length? Let us assume that capital P is the pumping length, and we will take the value of 7, that is P is equal to 7 for the pumping length. Okay. So we can consider any value. Over here I am taking P is equal to 7 as my pumping length. Okay. Next, the next assumption was we can divide the string that we have into three parts consisting of x, y, and z. Like we assume that the entire string is getting divided into three parts. First part is x, next part is y, and the last part is z. Right? So that is what I have shown over here, that s is getting divided into x, y, and z. Right? Now the next part is we have to take some example strings. We know that a string is constructed out of A's and B's, right? So okay, just a second, students. I don't know, my volume is getting reduced automatically. Let me join with my phone. Just give me a second. Am I audible?
Ma'am, you are not audible enough.
Now am I audible?
Now am I audible?
Yes, ma'am.
Okay.
Yeah. So
Yeah.
as I was
So as
saying,
I was saying, uh,
we are assuming that we
we are
have a
assuming
string
that we
AB,
have a string AB,
and we are
and
dividing it into three
we are
parts,
dividing it into
x,
three
y, and z.
parts, x,
Now we
y,
will
and z.
take a
Now
string
we will
like
take a
example
string
string
like example string
consisting of a's and b's,
consisting of
right?
A's and
And
B's,
since
right? And
p is equal
since
to 7,
P is equal to 7,
the number of
the
a's and
number of
b's will be
A's and
equal to
B's
7,
will
right?
be
So
equal to
7
7,
number
right?
of
So
a's
7
and
number
7
of
number of
A's
Ma'am,
b's.
and
Yes.
7 number of, yes.
ma'am, your voice is echoing, ma'am.
Just a second.
Okay, just a second.
Now is it fine?
Now is it fine?
Yes, ma'am.
I guess now it will be fine.
I
There is
guess
no
now it
echo,
will be
right?
fine. There is no echo, right?
Yes, ma'am.
So,
Okay.
um,
So, we are going to assume a string a to the power p b to the power p, since the value of p is 7. So there will be 7 a's followed by 7 b's. Okay. Now this is the example string that we are considering. Now we can have three cases over here basically. The first case is the y part. Since we are dividing it into three parts, some part of this will be x, some will be y, some will be z. Now what we can assume is y is in the a part. Let me go to the canvas, it will be more clear to you. So as I was saying, suppose I have 7 a's, 1 2 3 4 5 6 7, and 7 b's, 1 2 3 4 5 6 and 7 b's. So this is my string. Now since I'm dividing into x, y and z, I can assume that wait, these three a's consists of like x consists of this three a's, and then I have my y which consists of this 4a, and then I have this part as z. Now this can be one case. Another case is possible where y is in part in b, right? So if y is in b, what we can do is we can assume that this just a second. Yeah, so we can assume that this part is x, Suppose this is, sorry, this entire part is x, okay, and then this four b's are y, and then this three b's are z. Now this can be one consideration, right? Another consideration is also possible. What is that consideration? Which is y is in a and b. So y lies in a place where it consists of both a's and b's. How we can say that this first 5 a's are x, this 2a and this 2b, that is here, from here to here it's a y, and then rest of it is z, right? Now these three cases are possible. Okay. Acha. Now what we have to do next, what should be done? If you remember the steps, we have found a string such that the length of s is greater than p. We have divided it into three parts. We have seen all possible divisions. Now what we need to show is x y to the power I z is not an element of a. This is what we need to show. So how to show that? Just go here, go back, sorry, go back to this part. So xy raised to the power I z, suppose i's value is 2. I am assuming, or I am considering the value of I to be 2. So if i's value is 2, so we get x y raised to the power 2z. And in case 1, I am considering case 1, okay. So in case 1, let me go back to the canvas. If I want x y raised to the power 2z, what will be the value of the string? So x part, just let me write 3 a's were there in the x part. Achha, y part there were 4 a's. Now y raised to the power 2 means this 4 a's will be repeated. 1, 2, 3, 4. Then again 1, 2, 3, 4. And then I have z. Z was this 7 b's. So 1, 2, 3, 4, 5, 6, 7. So 7 b's. Fine. Done. Now what I have to prove, that this x y raised to the power 2z is not an element of a. How can I prove that? See, my a should always be, my L or language should always be of the form a to the power I, b to the power I. That is, number of a should always be equal to number of b's, right? But if you see in this string that I have got, the number of a is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 number of a's and number of b is 7. So number of a and number of b are not equal, which tells us that this x y raised to the power 2z is not a part of the language L. So the first portion is done. This first portion is done. We had to show that x y raised to the power I z not an element of a, and we have shown that, because here number of a's and b's are not equal, since this is not an element of L. Okay. Next, what we can try is, we can try to check for the rest of the two conditions. Do not go for this one, okay. Check the third condition. Let us see if the third condition is satisfying or not. So for this particular example, xy, length of xy is, let us see, length of xy is 1, 2, 3, 4, 5, 6, 7, right? Again, going to the diagram, it will be more clear. This was your x, this was your y, so it is 7. 7. And what is p? The value of p is also 7, right? Value of p is also 7. So in this particular case, the condition is satisfying. That is, xy, length of xy is less than equal to p. This condition is satisfying in this particular case. But you need to check this for all the cases, right? So if you go to some other case where y was a part of both a and b, which case? This case, this particular case where y was a part of both a and b. And now if you basically try to write x y, x y raised to the power 2 and z, for this case number 3, the string you are going to get is, for x you have 1, 2, 3, 4, 5. 5 is, so, sorry, 1, 2, 3, 4, 5. So X part is done. Y will be repeated. In Y we have two A's and two B's. So it will be repeated A, B, B, A, B, B. And next we have 1, 2, 3, 4, 5, 5 B's. So 1, 2, 3, 4, 5 B's. Fine. Now again, this is not a like element of the language L, obviously, because the most important thing in the language was sequence of A's followed by sequence of B's. Now which is not getting followed over here. We have B's and again A, then again A, then again B. So it is not an element of L. Now what about the next condition? The next condition was the length of xy should be less than or equal to p. So here what is the length of xy? X portion is this 5, 1, 2, 3, 4, 5. This is x5 plus y portion is 4, AABB. So it's 9, 5, 6, 7, 8, 9. So 9 is not, 9 is greater than 7. So this condition is not getting satisfied, right? So again, the second condition has also been checked for not being satisfied, right? So first of all, we have checked for this x y to the power, like y raised to the power 2 z is not an element of L. Once you are done, you go for checking the next condition, that is xy less than equal to p. Now in some case you might see that this condition is getting satisfied, but do not stop there. Go and check for some other cases also. Now if you get a single case where this is not satisfied, you can just conclude, or you can write the conclusion that according to the rules of pumping lemma, we can conclude that the language L is equal to a to the power I, b to the power I is not a regular language. Okay. And if I just say you that don't use pumping lemma, just by looking at the language, you all should be able to see that, say that this is not a regular language. By now you should be able to say. Why? Because I have told you from the very first day, students, that for a regular language we do not have a memory. It's a finite machine. It has a finite amount of memory. It can store just a few things. It has not got such a infinite memory. So here, if the string is of this kind, a to the power I, b to the power I, you have to keep a check on the number of a's. You have to remember the number of a's and check whether the number of b's are equal to number of a's. But if you use a DFA or a finite machine for this purpose, a finite machine can never remember the number of a's it has encountered, and therefore we can say that a to the power I, b to the power I cannot be designed using a DFA, and therefore it's not a regular language. Okay, so just by looking at the language, by now you should be able to say that this is regular and this is not regular. So this is an example where a to the power I, b to the power I can never ever be regular. And for proving that it is not a regular language, we have used pumping lemma, and these were the steps that you have encountered for proving the same. Okay, is it clear, all of you, how we have done the entire thing, the procedure of the proof? Actually, is it clear?
Yes, ma'am.
Okay. So we're going to see one more example, just so that you all become quite comfortable with the process. Here we have another language. If you see, L is equal to YY. Now L is equal to YY is a language where we can say, in words you can say that it's a kind of a string which starts and ends with the same substring, right? So whatever there is at the starting, the same thing will be there at the end, and your y is consisting of zeros and ones, that is the alphabet set is zeros and ones. So just to take an example, we can have something like this: 0 1 0 0 1 0. Now this is something which is a part of the language because it's a repetition. This is y, this is y. So this is a part of the language, right? So I was just giving an example. Now, the same thing you have to do, you have to prove that it is not regular. So, first step, assume it is regular, assume a pumping length, and here again we are assuming the pumping length to be 7. And the string that we have to consider, write it in this form: 0 to the power p1 and 0 to the power p1. Why? Because we already know that the form should be maintained. That is a sequence of y followed by the same sequence of y. So this form, like 0 to the power p1, and then again repeat 0 to the power p1. And what is the value of p? The value of p I have considered as 7, right? Okay. So if the value of p is 7 and you just write it, what will be the like form? So you have 7 zeros, 1 2 3 4 5 6 7, and then 1, and then again 7 zeros, and then 1. Okay. So this is how you're going to write. Acha, next step is, what is the next step? The next step that we had followed in our previous problem was we divided the string into three parts x, y, and z, and we have considered different cases. Now this time I am not considering the all the three cases. You can go for all the three cases. I am not showing just the three cases. I'll consider just one case, and as you can see the zeros marked in red, I have considered these four zeros to be my y. So this is my x, these two zeros are my x, these four zeros are my y, and this portion is my z. Okay, this is what I have considered. So next what I'll do, next I'll take the same form, that is x y to raised to the power I z, and I'll consider I to be 2. So x y raised to the power 2 z, and again if you take the same string I have got over here and put it in this form, so what I'll get is x was 2 zeros, I'll put x exactly same, y was 4 zeros, so 4 zeros and then repeat 4 zeros, this portion gives you y, sorry, this portion gives you y raised to the power 2, and this portion, this black portion again, it's z. Okay, now you can say that here the starting and ending strings are not equal. Look at this string properly. Are the starting and ending strings equal? So by saying this we can say that x y raised to the power 2z is not an element of L, because this string is not starting and ending with the same set of strings. So the first condition is verified. It is not a element of L. Now check for the next criteria. Checking for the next criteria is length of xy less than p. What is the length of xy? This is x, this is y. So it's 6, right? If I'm not wrong, it is 6. So 6 is less than or equal to p. Why? Because p was 7. So it satisfies. But what I told you was, do not stop by checking just one case. Go for some other cases, because y can be any portion of the string. So just take another y, like consider another case. Over here if you see, this was my x y z, and this is the portion I have considered as y in my string. This is a portion I have considered as y, and okay, let me go back here and tell you, actually this is the portion I have considered as y. Okay, so here what I am doing is I am repeating it once again: 0 0 1 0 0 0 1 0. So this part is for y raised to the power 2, this portion is for x, and this portion is for z. But here again you can see that starting and ending strings are not at all equal, and therefore it is something which is not a part of L, right? So I can say that x y raised to the power z is not an element of L. Okay, and what about the next condition? For the next condition, let us check what is x, what is the length of xy. So length of xy will be 1 2 3 4 5 6 7 8 9 9. This is x and this is y, so it's 9. So 9 is never less than 7 or equal to 7, so it does not satisfy the condition. So the second criteria is also not satisfied, and once you get this, you can say or you can write that we can conclude that the language L is not a regular language using the norms of pumping. Right. So there are many more examples, basically students, where a few more examples, a few more types where you can get such a question where you're given to prove that the given language is not a regular one. So you can practice those at your home, and if you find any difficulty, you can come up to me. But more or less, the process that I have shown you will be same for all of them. Try to construct a string, break it into three parts, consider some cases, which portion will be why, and then try to prove that this thing is not an element of the language, and that will be enough to prove that your language is not basically regular. And obviously the second portion will also be, it will be easy for you to consider any case where this entire length of xy will not be less than equal to p, and that also is a contradiction, and you can say that finally, according to the rules of pumping lemma, the given language is not regular. Okay, so is this example also clear to you, or do I need to explain it once more, or is there any confusion or anything that I need to repeat? Then please do let me know. Okay, so I hope then it's quite clear to all of you. In that case, you all can actually leave and take your IMCRP test, right? Thank you so much.
Ma'am, excuse me, ma'am.
Yes.
Ma'am, the IMCRP is not working. The website is not opening.
Just wait for some minutes. I think it will reopen in few minutes.
Ma'am,
Okay.
if it does, ma'am, shall we give it in the chat box if it doesn't open?
You can give it in the chat box, but it will not be registered in the system unless and until you get to give the IMCRP exam. So
Ma'am,
basically, yeah,
yes, ma'am, yes, ma'am.
yeah, that is what you can give it in the chat box, but you have to give the exam at the end of the day. Otherwise, I won't be able to, upload your attendance.
Okay, ma'am. Ma'am, will you please wait for some time? Like, I'll try and then I'll inform you in the
Sure,
meeting.
sure. Yeah, sure. I'm waiting. Okay.
Thank you, ma'am.